Okay, so we're going to start out with the case where the source is stationary and the detector is stationary. So at time zero, the first wavefront is emitted, represented by this bar. It's going to move with a certain speed v wave. And after a time ts, remember you watched the first video that introduced all the notation that we're using. The time ts is the period of the source, which means it's the time it takes between when the first wavefront is emitted and the second one to be emitted. And so after a time ts, the second wavefront is emitted. During that time, the first wavefront is moving out with a certain speed, vw, and it's been moving for an amount of time ts. So the distance it moves is one wavelength, which is lambda w. So that's basically the situation after a time ts. The first wavefront moved a distance speed times the time. That's one wavelength. And again, the wavefront, that's, for instance, if you remember in the first video, this is the place where the density of the air, say, is the maximum, and then this is also the place where the density of the air is the maximum. So that's one wavelength, which is the distance between the two the wavefronts where the density is the maximum, for instance. That's what we could imagine what's going on. Okay, and we also said before that the relationship between the frequency of the source and the period of the source is this. The frequency is one cycle over the time it takes for one cycle to be emitted. And we also said that, as you see here, the speed is the wavelength over the period, and 1 over the period is the frequency. So you can write down the speed also as the wavelength times the frequency of the source. Okay, now after some time, I mean, we're not specifying exactly how much time, but after some time, the first wavefront reaches here, the second wavefront reaches here, but they always maintain the same distance between them, one wavelength, for this type of material, for this type of medium that we're talking about. And so the distance will always stay the same between them. They both have the same speed. Okay, after some time, the first wavefront will hit the detector that's at rest. So that's what happens at this point in time. And the second wavefront is one wavelength to the left of that. Okay, if you wait for after some time, the second wavefront will hit the detector. And so this time that we waited is basically the period that the detector perceives the wavefronts to hit it by, successive wavefronts to hit it by. So it's the time between when the first wavefront hit it and the second one hit it. That's what we're going to call then T sub D. That's the period that's perceived by the detector. Okay. So the distance that the second wavefront moved during this amount of time is one wavelength, and it was moving at a speed vw. And so the time it takes for the second wavefront to go between this point and this point, which happened during a time td, the time it takes is the distance over the speed. It's just a simple relationship between time and distance and speed. The time is the distance that it moved divided by the speed that it moved. And so the period that the detector perceives is the wavelength of the wave divided by the speed of the wave. Okay, so that's exactly what we found, that the period of the detector, the period that the detector perceives is lambda w over vw. But what is lambda w over vw? That's just the period of the source also. And so the period of the detector, the period the detector perceives the sound, is the same exactly as the period that the source is emitting by. And since the frequency is 1 over the period, so that means the frequency that the detector is perceiving the sound wave to be at is 1 over the period of the detector, but it's also 1 over the period of the source. and so it's the same as the frequency of the source. And so the frequency of the detector is exactly the same as the frequency of the source. In other words, the frequency that the detector perceives the sound wave, how it is, the frequency of the sound wave, the perceived frequency, is exactly the same as the frequency that the source is emitting the sound wave at.